All right, we're going to start another section here. It's 11.8, combinations. Now, I don't have all the handout here, just the part that's that we're going to use. It's important. Now, the idea here is we're going to create a combination is different from a permutation in the sense that for a combination, order does not matter. The easiest way to think about a combination is to think about a group of people. Okay, a group of just a group. There's no order to the group. You might have three people, like John, Joe, and Jack. Okay, John, Joe, Jack. Doesn't matter. This is a group of three people. It doesn't matter if I list them as Joe, John, and Jack. It's still the same three people. It doesn't matter how many ways I arrange these. The fact is I can arrange this in these three people in 3 factorial ways. But it is still the same three people. So there's only one group of those three people. It's the same three. So the idea is that we're going to take a permutation, and since it's order does not count, when I create a permutation of these 3 objects, I have to divide out the 3 objects. Okay, the 3 factorial, because that's how many different ways you can arrange them, but all arrangements are the same. Okay, it's like when we worked with before, when we had the letters, like the DID. You interchange this with this and you get the same word. It doesn't matter which D is in which place. It's the same word. So in that sense, we're creating duplicates here. These duplicates. So we're going to take our permutations and divide out the number that we were taking. In other words, the number of items that you're actually trying to form this permutation with. And we're going to call it a combination now, but the same R, and divide that out. So we're going to take our permutations and divide out in a sense, what we would consider duplicates, because the order of those R elements does not matter where they are in the permutation. They create, as far as we're concerned, it's the same permutation. Can't tell the difference. So you divide it out. So here's our general formula here. Okay, that's when you put that NPR in its place, which is n factorial over n minus r, you get this thing. So let's do an example here. Number 2, there are 10 questions on a multiple choice exam. The instructions on the examiner to pick any 5 of the 10 to answer for credit. So we're going to take 10 combinations 5 at a time. So in other words, one student might pick, his order might be 3, 5, 7, and a 2. Let's say he picks a 4 here at the end. So he might do these questions, okay, in that order. He might pick his that way. And somebody else might say, well, I'm going to select question number 3, 7, 4, and then do my 5, and then do a 2. Those would be the same. Okay, those would be the same questions. So the order in which you list those questions doesn't matter. The order isn't important. The fact is that they're there. Same questions. So if we're going to do this counting, then we have to consider that that order does not matter, and that's why it's considered a combination. If order mattered, the order in which person did the problems, then that would be a permutation. Okay, these are permutations, this and this. If order mattered, then these would be different. But if order does not matter, these are the same. It's the same group of numbers. So we're not looking at any order here in either one of these. There's no order. Okay, order does not count. That's the real difference with these combinations as compared to the in a combination, order does not count. Or I shouldn't say count because we're counting things. I should say order does not matter. Okay, it does not matter when we do our counting. And that's what a combination is. Okay, for a combination, order does not matter. So that's what we have here. Anyway, here's our number, and we could calculate that. Let's see, we'd have a 10 factorial over. We got 10 minus 5 factorial and a 5 factorial, which is 10, 9, 8, 7, 6, 5 factorial over 5, 4, 3, 2, 5 factorial. 5 factorials cancel, and I can do a little bit of work here, get rid of that 10. Let's see, I get rid of that, make it a 2, get rid of that, make it a 3. So now it looks like I just have a 3 times 2 times 7 times 6, which is what? 6 times 42 is what? 264, right? No, that's not right. Okay, let me erase that. It's close, but get sloppy there. Okay, let's see. 6 times 42. 6 times 40 is 240, and 6 times 2, so it's 252. Okay, anyway, there's your, and I'll double check that one. Okay, so let's continue. An ice cream cone. You can have 3 flavors, and there are 44 flavors to choose from. How many different cones are possible? Well, this is not a 44 permuted 3 at a time. It's not, because you have to think about this. Let's say you had the 3 flavors, like chocolate, vanilla, and strawberry. To most people, it wouldn't matter which order they were in. Which one's on top, the bottom, or the middle. You've got the same 3 flavors. So we're not talking about the order of these flavored ice creams. We're talking about the fact that they're there. So you wouldn't have just a permutation. You would have to take that and divide it by the 3 factorial. And that's where we get the formula that we're working with over here. So it's going to be that 3. Let's see. You're going to have, well, this is the same thing as C with a 44 and a 3. That's what it is. Anyway, it's the 44 factorial over 44 minus 3 factorial times 3 factorial. So although the numbers look big, you shouldn't be scared. This is 44, 43, 42, 41, and that's where I'm going to stop. 41 factorial, because down here I have 41 factorial and a 3 factorial, which is a 6. That cancels with that 41 factorial. So I really just have this, and I got a 7. So this isn't bad at all. It's 44. It's 43 times that 7. So I'm coming up with a 13 244. It's still a heck of a lot of ways to create an ice cream cone, 3-flavored ice cream cone. But it's not 44 permuted 3 at a time. It's nowhere near that number. Okay. At the hot dog joint, you got 5 drinks, 6 sandwiches, 4 sides. Customer has to come in and order 3 different drinks, 3 different sandwiches, and 3 different sides. How many different lunch combinations are possible? So he's coming in to, looks like he's ordering maybe 3 meals. And in those 3 meals, he has to have a different sandwich, and a different side, and a different sandwich. Or maybe he wants to know how many ways he can do this. So we'll come in here. So this is a multiplication problem because you got your sandwich, you've got your side, and you got your drink. And we're going to take the number of ways to pick a sandwich times the number of ways to pick a side times the number of ways to pick a drink. And that'll give us our total. So this is the multiplication problem, multiplication principle. So here it is down here. I've got it written out. It's in different order. I got the drink, sandwich, and the sides. Okay, so the drink, how many different drinks are there? 5 kinds of drinks, right? Number of ways to choose a drink. Well, he's got to do 5, choose 3. And he's got the sandwiches, 6 types of sandwiches, times 6, choose 3, times, and you got the sides, 3 different sides, 4 sides. Okay, so 4, you gotta pick 3 at a time. Okay, so and again, these are combinations because if you pick 3 of those drinks, it doesn't matter how you order them up. Okay, a Coke, Pepsi, root beer is the same as a root beer, Coke, Pepsi. Okay, the order is not going to matter when you pick those 3 drinks. It will not matter. So, and of course, when we combine all these, let's see, this will be 5 factorial with a 2 factorial, 3 factorial, and then a 6 factorial with a 3 factorial, 3 factorial, and then a 4 factorial with a 1 factorial and a 3 factorial. Okay, so that's some work, but let's see, I'm going to bring it over here. We got 5 factorial. So I'm going to go 5 times 4 times 3 factorial, and then you got the 2 with a 3 factorial, and then you got a 6, 5, 4, 3 factorial over 6, and then that 3 factorial, and then you've got a 4 times 3 factorial over 3 factorial. 1 factorial is 1. Okay, so we got some canceling here. Let's see, you're going to go with that and that, and you're going to go that, and that's going to go, that, and that's going to go. What else is going to go? We're going to get rid of that 6. We're going to get rid of that 2 with that 4, make it a 2. What else here? I think that's about it. Okay, so 5, 2. We still got another 5 in there. And a 4. And a 4 out on the end there. Over here. Which gives, and let's see, 10 times 20, 200 times 4 is 800. Okay. So, it is a big thing when you read the problems is you have to understand that whether or not you're working with a combination or just a plain old permutation. And remember, when you bring these meals home, you pick them up, you bring them home. It doesn't really matter how, when you've got the sandwich mixed in with the, I mean, how many different sandwiches can you pick? When you've got 6 sandwiches, you're going to pick 3 of them. It has to be a combination, because ordering the sandwiches, lay them out on the counter, and it's the same 3 sandwiches no matter how you order it. So if you just did factorial with that, 3 factorial for those 3 sandwiches, they'd all be the same. Same 3 sandwiches. Doesn't matter how you order them or line them up. So that's, again, why we are taking, when you look at a problem, you have to make that decision if it's a combination or a permutation. And that's usually the hardest part. Okay, you got the hot dog stand now, and he's making a sandwich, hot dog. He has 5 different condiments, and he's going to use 3 of the 5 on a hot dog. How many different hot dogs can he make? Well, you can see how that's a combination, because it doesn't matter how you put together the hot dog, as long as you're using the same ingredients, the same condiments. You can put ketchup, mustard, and relish, or you can put relish, ketchup, and mustard, or you can put mustard, relish, and ketchup. It doesn't matter how you're going to put those on the hot dog. It's going to be the same. I mean, some people might say it's different depending on which order you put it in, but it's really not. I mean, ultimately, it's the same hot dog. So you can only do that. Then you're going to take 5. You're going to choose 3 condiments at a time. So you'll have this 5 factorial over 2 factorial with a 3 factorial. Okay, because notice the 2 and 3 always add up to the 5. And over here, when I did these problems, 1 and 3 made 4, 3 and 3 made 6, 2 and 3 made 5. See how they all add up in here. That's a fast way to do these combination formulas here. Okay, so here, I think I already did this one over here, and the first one I did here. What did I? Well, I didn't actually show that number, so let's just do it. 5, 4, 3 factorial with a 3 factorial and a 2. So you're going to come up with that canceling. 20 over 2 is 10. So there's really only 10 different ways to make that hot dog with those 3 sides. All right. Now we got a couple other problems here. How many sums of money can you form with a penny, a nickel, a dime, a quarter, half dollar, and a dollar? These are all coins. Assume that a sum can be formed by adding either no coins together. Okay, so you just pick a coin, that's it. You're not adding any coins together. So you just pick one of the let's say 1, 3, 4, 5, 6. We've got 6 different coins. Okay, all together. So now let's look at this. How many different sums? Well, okay, we already saw that you might pick 1 coin. Okay, so if you just pick any 1 coin, how many ways can you do that if you have 6 coins? Well, 6. Okay. In other words, you're taking 6 coins 1 at a time. Then you're going to take over here, okay, let's pick any 2 coins and add them together. That will give you a sum. This is a sum right here. The first one is a sum, but it's only 1 coin. The next one will be 2 coins, any 2 coins. And notice order, this is a perfect example where the order doesn't matter, because you can add a nickel and a dime, you get 15 cents. You can add a dime and a nickel, you get 15 cents. So we don't want to do that twice. It's the same sum. So that's why we're using a combination. The combination will eliminate that duplication. Okay, then you're going to add, because it's another way to get a sum. You're going to take 3 coins at a time. Then you're going to take 4 coins at a time. And you're going to take 5 coins at a time. And finally, if you want, you can add all 6 coins together at a time and figure out. Now, if you took them all together, there's only going to be one sum, right? This is 1, whatever that is. I'm not looking for the sums. I'm just looking to see how many different sums there are. It'll be one sum because you got all 6 coins added together. It's one number. So, well, let's look at our numbers here. We've got 6 factorial over 1 factorial. Oh, I'm sorry, 5 factorial and a 1 factorial. Then you have 6 factorial over 4 factorial, 2 factorial, and a 6 factorial over 3 factorial, 3 factorial, and a 6 factorial over 2 factorial, 4 factorial, and a 6 factorial over 1 factorial, 5 factorial, and a 6 factorial over 0 factorial, 6 factorial. Over here, this gives us 6 times 5 factorial over 5 factorial. This gives us 6 times 5 times 4 factorial over 4 factorial 2. And 6, 5, 4, 3 factorial over 3 factorial. And I'll write this as a 6. And 6 factorial, 6, 5, 4 factorial over 2 and a 4 factorial. And 6, 5 factorial over that 5 factorial. And finally, this one, I think we can remember 0 factorial is a 1, so this is 1 over 1. Okay, over here we got, I'm going to do some of this canceling now because that's, that's what I live for, canceling. 1, 2, 3 cancels, 4 cancels, 5, there you go. And we can also cancel something else here. We can get some other cancellations here. 2, well, I better do that with my red pen here. 2 into 6 is 3. And this 6 cancels here. That's nice. 2 into that 6 is 3. Still got a 6 there. No, okay, so we have all together now. We got a 6 plus 15 and 20. And in here, what do we have? 3 times 5 is 15, another 15. And then over here we got another 6, and then plus a 1. All right, add them up. What do we got? 21, 41, 56, 62, 63. So there are 63 different possible sums you could make with those 6 coins. We could have answered this by actually trying to find all those sums. I don't think that would have been efficient, and we probably wouldn't have gotten all of them. That would be a lot of work to keep track of all that. It's possible we could have, but I don't want to try it that way. Okay, here's another one. Our last problem. How many 4-man committees? When you see that word committee, you know you're working with a combination. So 4-man committees. 2 men of each nationality to be selected from 8 Germans and 9 Frenchmen. Okay, so we have these 2 things happening here. We have the Germans and we have the French. And we're going to figure out how many, first of all, how many ways you can select the 2 from the Germans. Well, they have 8, and we're only going to select 2. And for the Frenchmen, they have 9, and we're going to select 2. Okay, so if all we wanted was that, then we'd have 2 separate answers. But now we're going to join them together, okay, because we're going to make a committee out of these. So this is a number of ways you can form the German committee, so to speak, and this is a number of ways you can get that French committee. So if we multiply those together, we're going to find a number of ways we can find a German/French committee with 2 from each. Okay, so this will give us the number of ways we can get that done. So let's see if we can get an answer here. 8 factorial over 6 factorial 2 factorial and times 9 factorial over 7 factorial 2 factorial. So that's going to give us 8 times 7 over 2 times 9 times 8 over 2. That's going to give us 4 times 7 times, that's a 9 times 8, 4 times 9. All right, that's where I stop, and I write with my calculator. I got 1008, like that. Okay, so that's it. Combinations, interesting. Now, remember, may not have mentioned this before, but all of this is, this counting, all this stuff counting is so that we know how to calculate probabilities in a better way. We're better probabilities. We're in a better position to do, because remember, when you're doing probabilities, you're always counting things because you're finding the number of ways something can be done. And then you're finding sample space numbers. Okay, sample space numbers. So there it is.